their brownies.
So let's start.
Oh, you're on here.
So welcome everyone, and I'd like to welcome everybody in front of their screens all around the globe. Maybe on the International Space Station as well. So my plan is to talk for about 59 minutes and 59 seconds and let 1 second for questions. So I'm talking about discrete stochastic well-mixed chemical systems under the law of mass action, and I'm interested in averaging or the quasi-steady state assumption. Okay, let's put it another way. So I got interested in what are the chemical systems where you can compute the equilibrium distribution, and why this might be interesting beyond the academic curiosity is that you can use them for averaging. So if you have a chemical system where the natural timescales are well separated between a fast and a slow timescale, then you might want to do what is called averaging or the quasi-steady state assumption, whereby you're really interested in the slow reactions and you set the fast reactions, you say that they reach the equilibrium distribution in the time interval when the slow doesn't really change. And so you can then use this the equilibrium of the fast reactions in something like the messenger RNA or protein expression rate A. So you compute it as the average between two states G and G star. So state G and G star of a gene, which is expressing protein at different levels, and then you take this average. Okay, and so my aim is to catalog all systems where you can compute the equilibrium distribution so that actually you can do the quasi-steady state approximation. And so from now on, essentially all the reactions on all my slides are in the fast time scale, so I don't ever talk about the slow reactions. And so to clarify notions, there is something called quasi-equilibrium approximation and there is something called quasi-steady state. What I do is the quasi-steady state approximation. So if you look at the usual simple enzymatic kinetic problem, then the quasi-equilibrium approximation or assumption says that whenever you have a reversible set of reactions, you assume detailed balance. So the forward flow is the same as the backward flow. Whereas in the quasi-steady state approximation, you assume that C, so C dot is 0, so C doesn't change, so C has reached the equilibrium, which then means that the influx is the same as the flow out, so the sum of these two equations. So the quasi-equilibrium is when each pair of reversible reactions is balanced, which is detailed balance, which is called thermodynamic equilibrium in the physics literature. The thing is, though, that this imposes conditions on the rate constants, and specifically on circles, you have to have something. So the rate constants have to satisfy certain criteria, which are called Beck-Scheidels condition, and this rules out flows on cycles. And I don't want to do that in the QSSA. Although it might not be physical, what I'm thinking of is that it might be that there is flow around a cycle because there is some kind of energy input, so there is ATP influx, which propels such circular thing forward. And so the words equilibrium distribution and stationary distribution are synonyms, right? And so I don't talk about quasi-equilibrium. And there's a third notion, which is called quasi-stationarity, which is, so it's a completely different thing, which is when you have a system which can go extinct, and you look at the system right before it's going extinct. So you condition on that the system survives, so there is whatever species hasn't gone extinct, and you look at the time invariant distribution just before this happens. So given that there is no extinction yet.
So in particular, since you want to think about these slow, fast applications, quasi-equilibrium wouldn't even make sense because your slow variables could certainly be putting your fast variables out of thermal equilibrium, but it would make more sense to look for a stationary state as you're suggesting, right?
Yes, but then you have to look at sometimes linear combinations which are kept constant, and it's not particular species. And so the outline of my talk is that we've done with the introduction here. So I'm going to go through simple biochemical reaction systems where you can compute the equilibrium. Then the major contribution here is what happens if you have a gene expression system where dimers control the expression. I'll then summarize so compare different gene expression systems, and that's different thing, whether you can, if you know the equilibrium distributions of small Markov chains, can you put them together and compute the equilibrium distribution of a big Markov chain? And then towards the end there will be some more interesting stuff and more open questions. So it turns out that whether you can compute the equilibrium distribution of a reaction system or not depends on the state space of your Markov chain and not really on how the chemical reactions look like. And so the easiest case is if your state space is a linear graph, so in this case an infinite linear graph, because then stationarity can only happen when you have detailed balance on every pair of reactions. And so one chemical example is the burst-death process when protein P is generated, and it is well known that then this has an equilibrium distribution of the Poisson distribution. Okay, so your linear graph might also be finite, so from pi naught to pi n. There are many examples like isomerization, when a molecule has two forms which turn into each other, then the equilibrium is just a binomial distribution. Or you might have transcription factors binding to multiple copies of a gene. So you have many genes, identical genes, like plasmid bond genes, and many transcription factors, and then your state is how many genes have bound one of these transcription factors. And then on the left-hand side, there are 0 bound states, and the far end, then you have the minimum of how many genes and how many transcription factors you have. Another example is dimerization, so how many dimers you have increases along this line. And two very simple cases when your path is just 2 states or 3 states, so you have a gene which can bind the transcription factor out of a pool of many transcription factors to turn into this active form, whatever form, or so that's on the next
All those
slide.
solutions are actually detailed balance solutions, is that right?
All solutions are detailed balance, so there is no other way you can get an equilibrium distribution. So here is your chemical system, so you're either in this state or that state, so we have just one gene and T transcription factors, and the gene either binds one of them or doesn't bind them. And so this is how it looks like with chemical reactions, and then it's completely trivial that this is the equilibrium solution. Okay, so what if transcription factors you must bind 2 transcription factors to, let's say, turn on the gene, and they must bind in a sequential order. Then this is the reaction system, and again you can compute the equilibrium distribution. It's not too important at this point how it looks like. So that's about linear state spaces. You can also compute the equilibrium distribution for circular state spaces of Markov chains. So there is this technical note which does that. It's somewhat more complicated than you would think, and it turns out that there is an explicit formula, this one, how the equilibrium distribution looks like on a circular Markov chain when transitions are only allowed between neighbors. And the question is whether you can find a chemical system which has this one as a state space. Yes, there is.
I mean, my intuition with this is, I mean, when you have the linear chain, then basically, once you break it down, there is a detailed balance solution. It's easy, right? You're just doing something recursive, and then for the circular case, you have to allow some constant flux. So now you have almost detailed balance of some unknown constant. You can still solve recursively. Is that how these solutions work?
So it's done with induction over the number of states.
No, okay, it's more complicated.
And it's more complicated because probability can flow around.
But at a constant rate, right?
Yes, yeah. And so one chemical system, actually the only one which I could come up with, which has a circular state space, is that you have a gene with 2 binding sites, and transcription factors can bind independently from each other. And so, again, we have just one gene and T transcription factors, and this is then the chemical reaction which we are looking at. So what's interesting to note is that there isn't much correlation. Also, by looking at this, you don't really realize that that is how the state space looks like, and vice versa. And what I'm saying is really, if you want to compute equilibrium distributions, it seems that what is important is the state space. Okay. And there is a fair bit of cheating here, because I specify that I only have one gene. So if I had two genes, then it would make it much more complicated and I wouldn't know how to solve it. Which means that I'm not solving the equilibrium distribution for this chemical reaction system. I'm only solving it for a particular stoichiometric subspace of it.
Well, yeah, seems to play solved here, isn't it? I mean, given the concentration of friction factors, it seems to be fully solved. So what's not solved here? I'm confused. Why isn't this exact? Or why isn't this just the full system?
I'm not looking at ODE, I'm looking at the stochastic discrete model.
Right.
And so it's not the steady state of the ordinary differential equation, what I'm computing. So if you had two genes.
Wasn't the last slide for the circular state,
Yes.
circular system?
Yes.
And wasn't that the exact answer?
Yes.
So what's different here?
So if you had two genes, then the state space would no longer be a circle. Then it would be a direct product of this one with itself.
Yeah.
But there would also be the problem that transcription factor bound to one of the genes influences the rate of binding at the other gene, because
Right.
then it's removed from the pool.
But you can go in some regimes if you have enough transcription factors.
But that's not what I want to do, because it's
No, I'm saying there can
Sure.
be different regimes where
Sure.
you can study. So you're looking here at the steady state distribution of the Markov chains, right?
Yes, and
Okay.
analytical, and I want closed forms because then I want to
Yeah, it's good,
compare
it's
them
good.
later.
And have you?
This is deficiency 0, right?
So I think it's deficiency 1. So
Is it?
I computed it just
okay.
yesterday or something.
Have you also looked at the case where you can have repressor? You see, a transcription factor binds
Yes.
to activate.
Yes.
You can also have repression, that is, the molecule comes
Yes.
and prevent the binding of the transcription factor as long as it is here, and then it can go away.
No, because it's just too complicated. So one of the reasons why this talk is about simple chemical systems is that it becomes extremely hard to just get a grasp of the Markov chain state spaces, and that's why not.
Okay, it should not be the right reason. I mean, the right reason is to look at what we have, and going into some mathematical simplification is interesting because you get results. This should not prevent you to look at the real question from reality.
No,
Because-
it's the other way around. So I limit myself to analytical exact solutions.
You
That's
should
what I'm
not.
saying.
You should not. That's what I'm saying.
But
So-
this is topic of this talk.
No, but I understand. I understand. But what I'm saying is that, so you think that with adding a single repressor, would all of this would not be able to, you will not be able to get an analytical solution?
I wouldn't know how to do it. And
So
yes,
what's
so yes, it's not easy.
It's almost analogous to taking a 1D problem and making it a 2D problem, right? I mean, it's
And then it's
Yeah,
taken to
yeah.
3D.
So
So this is not 2D, and then you want to take it to 3D.
Yeah, okay, you're right. It's like adding a
Oh, and by the way, what I haven't said is that, so computing the equilibrium distribution in a Markov chain is just solving the pi transpose q equals 0
Yeah.
equality. So you can do that numerically whenever you want. So my goal here is to do it symbolically, and then get formulae in the end which are somehow informed.
No, I understand. It's very important because here you get the dependency with the parameter, which is great.
Yes, yes, exactly.
Well, also, you had said at the beginning, which maybe you missed, but he said at the beginning that his motivation here is that he wants to use these to do steady state approximations in bigger models to simplify the equations.
Yeah, because we looked at this with the repressor. It was very hard. We looked at path in the Markov chains, but so maybe you have a clever way to look at it. This was my push.
Okay, let me go on, and you will see that the complications increase incredibly. And so this is one of the points of this talk, to explain that it's actually hard, and so it becomes combinatorially hard very quickly.
Sure.
What's next? Okay, and so the next complication is what I call ladder-shaped state spaces. As you can see, there are two parallel branches connected with transitions between them. So one chemical system you can think of is that there is a gene which is switching between two states, well, off and on states, and in the on state it produces a protein. So there are arrows pointing upwards on this branch, and the protein can be degraded both in the off and in the on states, and then go down. So this system was studied in this paper, not just the equilibrium distribution, but the time evolution of it. Okay, another system studied by Lamon Grima, who was here at our opening workshop briefly, when you have a transcription factor expressed by a gene itself. So the gene can express this T at two different rates, whether it's bound or not, and then this transcription factor then regulates its own expression. And so the corresponding state space looks like this, again, this ladder shape. What is tricky here is that so the transcription factor can be degraded both in solution and also when it's bound to the gene G. And there are here is two other papers which looked at similar ladder-shaped state spaces. And so what the method is to deal with these cases, and in general case it gives you the time evolution, but then often only the stationary solution, is to define the probability generating function for the system. So you define two probability generating functions, one for the upper branch, one for the lower branch. And then you can write the chemical master equation as partial differential equation in these two generating functions. So on the left-hand side, you have dt generating function upper branch, and the dt of the generating function for the lower branch. And on the right-hand side, you would have functions of this generating function and also the connection between the two, so coupling between the two. And there will also be very often the derivatives with respect to the variable z.
So, but if you use that approach, you don't get a joint distribution of probabilities in the upper and lower ladder, right?
You do. So I'm not saying it always works, but this is a method which has often worked. And so what you do is then you write down this PD for your two probability generating functions. And very often people can express an explicit solution in terms of special functions, so-called hypergeometric functions, confluent hypergeometric, and these point functions. And they might not say much about the asymptotic behavior, but at least you can ask a computer program to evaluate it.
I'm saying conceptually, I mean, if you're doing a probability generating function just for a subset of the state space, isn't that sort of like a marginal? I mean, that it can't capture correlations between the two subsets of state space. If I have two random variables and I sort of write down an equation or probably generating function.
But you do it for the two variables. You get a PDE in usually in T and the J or whatever it has. Usually this is what you're doing. You multiply by X to some power. So I guess this is what you meant.
But my point is that there being two. Right? One thing if you said I'm going to make a probability generating function for the whole state space, but
you have T, X, and Y. So you have usually for the joint probability.
So we have two variables, how many of the proteins you have, and what state you are, whether you're on the upper or lower.
oh, sorry, I get it. So then, okay.
And so I got interested in the following system. You have a fixed number of T transcription factors and one gene, but these transcription factors form so they come in monomer forms, but they have to form a dimer, and only this dimer is allowed to bind to the gene G. And what I'm interested in is then what is the probability that you find a gene in the bound or the unbound form? So the marginal distribution of being in the upper branch or in the lower branch. And what's different now is that that this is finite. So there is a finite number of transcription factors, and this generating function method doesn't work very well because of that, because of sums are not infinite. And so it took me months and months to figure out a way to compute this. And this is the answer. And what's interesting is that the method I used to compute it has such a high error rate that the first term, so it's t to the minus 1, but then the second term is t to the minus 6 plus, so to the t to the minus 2. That's not nice. And the other thing is that, so I can't capture the dependence on kappa 1 and kappa minus 1. That's completely missing from my formula. So it's only the kappa p and kappa p.
So can you say one word? How do you get this?
I will say many words about it. Okay. And so there is another general method to compute equilibrium distributions in chemical reaction systems, and I'm going towards that direction. So, but first let me introduce what, they are called, it's called product form stationary distributions. So, so let me discuss what it means to have a complex balance, steady state, and now we are back to the ordinary differential equation world. So C dot evolves according to the usual reaction rate equation. S is the stoichiometric matrix, so beta is what's on the right-hand side of every reaction, and alpha is what's on the left-hand side of every reaction, so the products and the substrates. And so we can have steady state, so you know what steady states are, that's when C dot equals 0, so those concentration vectors. And complex balance steady states are a special form of steady states, which means that you have a strictly positive concentration vector, such that for every complex, and I hope now you know what complexes are, for every complex the outflow, so the sum of the reaction intensities when the complex is in the alpha, so the complex is the substrate side, is the same as when the complex is produced. So for every complex you have to have this balance, that influx to the complex. So this sums over all reactions, this is also sum over all reactions. So the influx to the complex is the same as the outflow. And one way how you can prove that your system has this property, that it has a complex balance steady state, is the well-known efficiency zero theorem of Martin Feinberg. So this is a necessary condition. There might be many more systems with this property, but this is how you can prove that there is a complex balance steady state. So your system has to be weakly reversible, and it also has to have efficiency zero. And if these two conditions hold, then you will have a complex balance steady state in every compatibility class. It will be unique and strictly positive. And so the efficiency is a property of the network. That it's a number, how you can compute it. And weak reversibility is also just a property of the network, so you can look at the network graph, check whether these conditions hold. And so there is a theorem by David Anderson and two co-authors, which basically says that if you have a chemical reaction system where the ODE has this property that it has, so the ordinary differential equation has complex balance steady states, then the stochastic discrete version of the same chemical reaction network has a nice stationary distribution, which is the product of Poisson distributions, essentially. So what's happening is that you pick a C, which is the complex balance steady state from your ordinary differential equation, and use this C as the parameter in a Poisson distribution. So we have n species, and the value of species I is xi, and so the probability that in your state x you have species xi for all the I different species is this product. And well, I don't give an explanation why this is true. I don't know whether there is an explanation at all. So this is the case when your state space is irreducible. Then this is the unique equilibrium distribution. If it's not irreducible, which happens usually when you have stoichiometric compatibility classes, then on each of these compatibility classes gamma, there is an equilibrium distribution of almost of this form. So there is some kind of normalizing constant, which is now no longer e to the minus ci, where again c is the steady state, the complex balance steady state of the ODE. And again, it looks like this form, so it's a product over x is the variable, so xi is what is the probability that your vector x has in the equilibrium distribution, and then it depends on the individual coordinates in this form. Okay. And so this formula holds for every compatibility class, and throughout the entire space you take a mixture of these depending on the initial state. Okay, and it so happens that my system satisfies the deficiency zero theorem, and the product form stationary distribution result holds. And so this is my stationary distribution in my compatibility class. So I assume that I have, again, this is, so back to where we were. So this is my chemical system. I have one gene and T transcription factor monomers, which then form dimers, and then the dimers bind to the gene. And so I have to specialize. So this is what comes out from the product form stationary distribution. Whatever has a cap is the ODE complex balance steady state, and whatever doesn't have a cap is the state in the Markov chart that we're looking at. And so what I need to make sure is that the sum of G's and G stars is 1, and also the number of monomers is just how many, what is the total number of transcription factors minus 2 times the dimers minus 2 times how many of the dimers are bound in this in the bound form. And so what I'm interested in is the probability that G star equals 0, and the probability that the gene is in the unbound form, and the probability that the gene is in a bound form, and for that you just need to sum these kind of terms. So I need to sum along the branches in my ledger. Okay. And what? Because of these conservation laws here, what turns out to happen is that, so you sum over all possible dimer counts from 0 up to T divided by 2, so the total number of transcription factors divided by 2, because that's potentially how many dimers you can have. And you just sum the number of monomers and the dimers, these are these two terms. And because of the conservation law, so you sum for the number of dimers, so you have these constant time to the power of the dimer count divided by dimer count factorial, and then the number of monomers is, so as you increase the number of dimers, then of course the number of monomers decreases. And so when you sum for D, there will be something increasing in D, and there will be something decreasing in D. And I want to compute this sum.
And what is this little GT in front of everything?
So the GT hat
Little
is,
t. Yeah, this one there was a little t.
and also these guys. So so like I said, the parameters to this system, these hats are the complex balance steady state of the alternate differential equation, and GT is so that's the steady state of the total gene number, and I think that's just set to 1. I don't really remember, so okay, 2. Yeah, so one trick with this product from stationary distributions is that you can actually pick whatever concentration. So even if you want to compute the equilibrium distribution in a given compatibility class, you can pick your steady state, you can keep your complex balance steady state from a different compatibility class. So that means that the total number of genes, so although in my stochastic system I have just one gene, I could have picked the gene for the parameterization from the ODE from a different compatibility class, meaning that I could have assumed that in my ODE there are 10 genes and not just one. And I think that's why you have, so GT means total number of genes, so free and bound together. And so anyway, the point is that I want to do a sum for D of these combinatorial things such that here there is something increasing in D and here there is something decreasing in D.
But you don't know C sub t either, right? Is that your normalizing constant?
C sub t, yes, that's normalizing constant, but you just normalize over these two things. So the sum of these two terms is 1, and that gives you C. And so the idea here is to use generating functions. So look at this function. So the exponential of something times z squared times the exponential of this thing looks like in the power series expansion as this term. And you can rewrite this as a sum just in n, so z to the power of n. And so what I'm doing is the Cauchy is called the Cauchy product of infinite power series. I hope that rings a bell. And so if you multiply two infinite power series, both are z to the power of something, then how do you compute the coefficient corresponding to z to the power of n? And this is how you compute it. So again, so this is exactly that sum that I had on my previous slide. So there is a sum in the diamond numbers from 0 to n½, and there is a number, an index which is increasing in this k, and the number which is decreasing because their sum must give n, and n is this exponent here. Okay, and now this is very good because the sum which I had on my previous slide, this tricky combinatorial sum, is now encoded as the coefficients of a power series of this function. And so what I really want to figure out is what is the coefficient, so of this function, what is the coefficient that corresponds to z to the power of t variable or term, and again what's the coefficient of the same function which corresponds to z to the t minus 2 term. And this is exactly the normalization that they just asked about. So essentially this is what I would like to compute. So the ratio between these two of these two coefficients, and again this coefficient is this number in a power series. So I wanted to do here these sums for a fixed t, and what I did is that I turned this sum into the coefficient of a power series of this function. So this sum is now just the coefficient in term n of that power series.
So is that the step that took a long time to find? I mean, that's not very natural to me to think to do that.
It is natural to do that. The question is, what do you do afterwards?
Fair enough.
And okay, so what do you do afterwards? So what we really want to do is compute the ratio between two coefficients in this power series. So the coefficient t minus 2 and the coefficient corresponding to t. And I don't know how you compute that. So what I did is that I computed two of them individually, and I took the ratio. So I just copied the same function from the previous slide. It happens to be the case that so in the ODE this is the steady state. So the dimer count looks like this so in the steady state, ODE steady state, the number of dimers is just t half minus square root t and so on, power series. And so maybe what I should say is that these computations are very complicated, and there are always these power series and error terms and so on. So at one point I given it up and I just started using Mathematica, because then you can just set how many terms you want to carry, and it makes it everything very easy. And so now what I said is that I want to compute the, so I have this function in Z, I want to compute its coefficients in this power series expansion, and how you do that is called the Cauchy integral. So you look at this function as if this was a complex function, so function over the complex numbers, and you do an integral, curve integral. So in order to get the nth coefficient, you divide by z to the power of n plus 1, and you do the integral around the origin.
It's like getting around coefficients?
Hmm?
So like getting around coefficients?
Oh, no.
Coefficients of a Laurent series, basically? Never mind, I take it from here.
And so if you want to do these kind of calculations, this area of mathematics is called analytic combinatorics, and there is this really entertaining, well, it's even entertaining group like Flageolet and Sedgwick, which does all kinds of combinatorial calculations using the trick that when you have a sequence of numbers, like how many, like Stirling number n or Fibonacci numbers or something like that, you encode them as the coefficients of a power series, and then you do complex analysis on these functions in order to figure out, let's say, how the asymptotic growth of these coefficients. So it's a really interesting technique, and so this is the thing that you do. So you do this Cauchy integral formula. So you divide by z, which means that you introduce a singularity at z equals 0, and you integrate around it in a circle. Depending on what the function is that you started off with, so whether this is an entire function, like in my case, or whether you already had a singularity, how you need to do the integral differs, and it turns out that the entire function, so what I have in my case is the worst case, because then the calculations are the least accurate. And so this is how the function looks like, and so this gene is the z equals 0, and so it has a saddle point here and a saddle point there, and the statement is that in order to compute this coefficient, you just integrate around this gene in a circle, and then how you do it is.
Sorry, why does it being entire make this calculation less accurate?
I can't explain it to you, so I don't know, you should go into read the book. So
Okay, thanks.
I don't remember because I didn't even need to read
That's
those
fine.
parts. So I don't know how it's better when you have two singularities. Somehow it helps you estimate how big your function is. Okay, and so there are calculations. And what turns out in the end is that, so the ratio of these two coefficients, so the coefficient t to the minus 2 and the coefficient t is just this number. And so with all these calculations, I figured out that they are almost essentially the same with a small error between them. And so the probability of the gene being in a state 0 is, well, this number which you get from the product form stationary distribution, and this number comes from the complex balance steady state of the ordinary differential equation multiplied by this number 1 plus something.
So
Okay.
how hard is it to get those coefficients in the next order terms? Are they like,
It's impossible with the method analytically. So there are very specific.
are they using like abelian or Tauberian theorems?
So what you're doing is that, so if you look at it in the whatever it's called polar coordinates, then you have to integrate along this straight line here. And in order to do that integral, you approximate this function, what you get when you cut across here, with a normal probability density function. And that has a certain error, and then it has certain tails, which has a certain error, and so on. And so these add up to the error term.
And so to understand what you did here, you let MATLAB calculate this, you look at what happened for large t, you calculated the ratio, and this is how you obtain your mathematical or whatever you have used, and then you obtain this identity. How do you get this identity of where are these points the MATLAB or Mathematica enters?
You need to do all kinds of series expansions,
Okay.
and then the question is where you cut that off. And you multiply, two series expansions together, and then how long exactly should your series expansion be so that it's still accurate enough and you still have a leading term which is meaningful. And I use Mathematica because when you start off, you don't know whether it's enough to carry 2 terms or you need to carry 3 terms and so on. Okay. So it's accurate modulo that you believe that Mathematica doesn't make calculation errors. Well, it's all symbolic calculations. Okay, and so now that we have 4 systems, we can compare them. So gene binds the transcription factor, gene binds the dimer, which form monomers, gene binds 2 transcription factors sequentially, and it binds 2 of them independently. And then the probability that the gene is bound is expressed by these terms. And what really surprised me is that, so the leading term is, so it's always 1 minus a constant times t to the minus first. And it actually really surprised me because when you have a Hill function, you know what Hill function is? Hill function, if you have a Hill exponent n, then this exponent would be minus n. So I at least expected that, let's say, doing the dimers or binding the 2 transcription factors, you would get an exponent which is not 1, but you don't get.
So in the first terms here, your mass action assumption results, and if you did an ODE assumption instead, or ODE approach, would you get your low order terms here?
Would I get the same from ODE
I mean, those are different, obviously, high order terms, but
I imagine, yes, the problem with the hill is that you assume that there are n+1 molecules reacting in one step.
right.
And if you cut it up to many sequentially, then you don't get the hill function.
You do get a function for ODEs for large numbers, I think, don't you? Binding.
I don't know. So what you might ask is when your binding is cooperative, so that means that you look at some extreme ratios of these coefficients, then in those limit cases you might get -2 here.
Mhm.
And so, okay, let me carry on. So, like I said before, we're computing the equilibrium distributions in chemical systems. So things that I haven't talked about are one thing that Ruth Williams at UCSD has been working on for a few years with Jeff Hasty, which is multi-class queuing systems and the equilibrium distributions of those. I don't have time to talk about them. What's interesting is that people think that usually assume that if you have different proteins in your cell and they somehow correlate, so the fluctuations are correlated, and people usually assume that that's because of an upstream reason, so that their expression is correlated. What Ruth Williams and co-workers figured out is that actually it might happen that the reason is downstream, so there is a bottleneck in an enzyme which breaks all of them down, and because of that you see correlations between different classes of proteins. This is why it's multi-class. Okay. Another general theorem which is good to keep in mind for computing the equilibrium distribution in Markov chains is the Markov chain tree theorem, which is not always very applicable, but actually the circular state space is a special case of its application. And there is another method which can be useful in simulating the equilibrium distribution, which it's called dominated coupling from the past. And this is something that David Anderson mentioned. So I have these two citations by Martin Hemberg and Mauricio Barahona from 2007 and 8. David, you might know papers which are more recent or not.
Wait, you're referencing me for
Yeah.
dominated
No,
coupling?
I'm not referencing you. I just heard that we were talking at one lunch or where you mentioned this method, the dominated coupling from the past. And so,
I don't think so.
you don't know this method?
No.
Really? Dominated coupling from the past. Anyhow, so it seems like it's a...
Very drunk at the time.
So it seems like it's a general method to compute the equilibrium distribution using the stochastic simulation algorithm. The problem is that you can't always implement it, so there are conditions that have to be met, and you can't always do that. Okay, and so it goes on. So we got interested in the following questions. So if you have simple Markov chains whose equilibrium distribution you already understand, can you build complex Markov chains by putting them together and still compute the equilibrium distribution? Or if you have a big Markov chain, can you perturb it a little and still know how the equilibrium distribution changes when you do this little perturbation? Okay, and so here is one perturbation which I propose. So you have two Markov chains, so one is XA and the other is XB. Both of them have a state which is labeled with 1, and I just glue these two chains together, keeping this. So I glue state 1 to state 1 and keep every transition to get this combined or glued chain X. Yeah, that should be straightforward what's happening, right? And so the question is, if you know the equilibrium distribution of this guy and this guy, can you compute the equilibrium of this one? And this is formally, so we have R states on the left-hand side, S states on the right-hand side. So these are indexed from 1 to S, and these are indexed from 1 down to negative numbers, and group 1 together to 1. And because previously we computed the equilibrium distribution of linear and circular graphs, if you solve this problem, then you can compute the equilibrium distribution in graphs which you get by gluing together linear parts and cycles and linear parts and cycles together. Okay. And how this goes is that it's rather, well, it's simple if you just look at the transition matrices. So the combined chain will have this transition matrix where QA and QB are the two separate transition matrices, reaction or transition rate matrices, and you have pi A and pi B, which are null vectors of the original ones. And so you say that it would be nice to put together pi A and pi B because this part multiplied by this part is already 0, and the elements here are 0 anyway, and the same holds for pi B. Just a question of what happens in this column. And it turns out that actually, yes, this is something you can do. So the solution to the equilibrium distribution of the combined chain is just that you scale the left-hand side and scale. So take a constant multiple of the left-hand side and take a constant multiple of the left-hand side, put them together, and make sure that in the shared state is state 1, where we glued, is the same in both states. So pi I, so this is in the combined chain, the equilibrium distribution I on the left-hand side, so which come from the chain A, is proportional to pi IA. So that's multiplied by constants. On the right-hand side, which come from the XB chain, they are proportional to pi IB. And state in the middle specializes to both. Okay. And there is a nice interpretation why this holds. And for that, you need to know what the ergodic theorem is. Do you know what the ergodic theorem is? I wanted to write this down on the web. So the statement is that if you want to compute the equilibrium distribution of the function f evaluate x, where x is the equilibrium distribution of the Markov chain, then it is the same as the time average of the integral of so you take the limit here, and these are equal surely. So this is the time average of the state of whatever the state does, and this is the spatial average, and these two things are equal.
What's it called?
Ergodic theorem. And then obviously we use the indicator function of state I, right? And so then that means the probability of being in a state in the equilibrium is just a time average of how much time you spend in that state. We will learn about this. And so what happens here is that if you're interested in the equilibrium distribution in the left-hand side, then you just follow the random walk of the state, and sometimes it will come to 1 and step to the right, and it does something, but when it comes back through state 1. And it means that you can cut out all the time which is spent here, because the behavior on the left-hand side is the same as the behavior would be in that individual once you have cut out this right-hand side. And then using this ergodic theorem, this is why the equilibrium distribution doesn't change if you just glue this one at one state to the other. Because the behavior, how much time you spend in any of these states, doesn't change if you just ignore or cut out those time intervals when you're in the right-hand side. And so the next challenge was what happens if you glue at 2 states. And this turned out into a complete paper. So this is interesting because there are special cases, like you have a big chain XA and you glue a linear path of just 2 states into the big chain A. So that just means that you have a big chain and you increase the transition rate between 2 states in XA. Or if you have a big chain and glue into it a linear path of 3 states, it's equivalent to adding a new state to your old chain XA and connecting it to 2 old states with transitions to and from those 2 states. So this is how this now looks like. We again have 2 states labeled 1 and 2, and 2 states here labeled 1 and 2, and we glue these 2 chains together. along these states 1 and 2. And we keep every transition rate, so when we have transition rates here and there, then those are capped, so the transition rates add up. And you would like to use these pi A and pi B, so the original equilibrium distributions in the new chain. And the statement is that you can do that as long as there is this proportionality condition. So if this condition holds, so for the old chains A and B, then what I said with gluing at one state, that will hold. That means that the new equilibrium distribution will be proportional to the old on the left-hand side and will be proportional to the old of the XB chain on the right-hand side. But if and only this proportionality condition holds, which is expressed in this statement, in this theorem. So the statement is that these three things are equivalent. So what we've just shown, or what I've just shown, is that if this condition holds for the two original chains A and B, then in the new glued chain that ratio will also be the same. But this is also true from BA, you can infer A. So if this ratio in the new chain is the same as it was in A, then it must have been that already B had the same ratio. Okay. And let me skip how we prove it. So we generalize this argument with the ergodic theorem using a regenerative structure of the Markov chains. And then we do a lot of calculations and arrive, let's say, so this is the main theorem here, that in order to compute the equilibrium distribution in the new chain, you have to solve this linear system of equalities where V, W, X, Y are these parameters, and these parameters express how likely it is that, I don't know, let's say starting from state 1 on an excursion which comes back to state 1, how much time you spend in I, and what is the intensity of leaving on such an excursion.
Are you proving these in general or under some assumption of having a chain? Because I see this like negative R plus 3, negative R plus 4, all the way to 0. Or is that just, how you're enumerating the state space?
That's just how I enumerate. So,
That's
so the chain on the left is indexed with the negative numbers, so that is 0, 1, 2, and then the other one comes 1, 2. Okay, and so this is a relatively interesting statement which comes out of it, even if you don't want to look at the complete solution. So if this condition, so if A fails, so it is not true, so if this condition holds, so these two ratios are not the same, then it tells you that the equilibrium in the new chain in state I relative to the equilibrium in the old chain XA, where it came from, is bounded by these two terms. And also the ratio in the new glued chain, so the pi1 over pi2 is sandwiched by the minimum and the maximum of these two numbers, which are not right. So the question is, what happens when you do two Markov chains at two states when you glue them together? And so we use the ergodic theorem for regenerative processes to deal with this case. We get explicit solutions in terms of quantities from the original chains, but these quantities, these parameters are not well known. So these are not usually things that people study. If you want to compute them, then you need to solve. So instead of solving the pi transpose q equals 0 equations, which is of this size, you have to solve this many linear equations of size r by r times r, and this many linear equations of size this one. And it turns out that the computational complexity is essentially the same. So it doesn't improve and it doesn't really get much worse, but it's certainly not an improvement. And the problem is that even though, so the argument might be nice that you just use this regenerative structure and this excursion through these Markov chains, even when you perturb a complicated chain by a simple one, so you have a big XA and XB is just 2 states or 3 states, then the calculations are complicated. So they will be complicated. So in other words, in the general case, it's not easy to put together 2 Markov chains and compute the equilibrium distribution. Okay. Interestingly, this has been somehow discussed and thought a bit further by somebody called Flora Menk, who sent me an email. So she's an Oxford undergrad who spent the summer, I don't know how much time, so research day in the lab of Richard Murray and worked with 2 of his PhD students. And just in 1 week time, so exactly on Wednesday, so she's going to present her results at the WinterQ Bio conference. So first she characterized all the graphs that you can get by gluing together linear graphs and circles at 1 state every time. So there are no surprises there. But what's interesting is that she found that in systems like this one and that one, this proportionality condition, so when you glue at 2 states and the proportionality condition holds, this A, then the equilibrium, let's say in the left-hand side of your state space, will be proportional to the original equilibrium, but if and only if the proportionality condition holds. And what she found is that this proportionality condition holds actually in a number of cases, and so I'm surprised. So why would it hold? So for me, this is an open question whether this happens frequently or not. And so does it happen?
Wait, so to be clear, I want to make
Yes.
sure I understand what you're saying. So, for the system that you just splashed, but now we're gone from, that doesn't hold. The condition does not hold?
So what I'm saying is that this condition holds in at least 2 systems, two chemical systems, which they found. And I see no reason why it should hold, but it does hold. And it means that you can compute the equilibrium in those 2 chemical reactions using this gluing argument. Or well,
Oh, you're saying why did I see?
Where are they gluing at for the examples you showed?
I should draw it, shouldn't I? So that system looks like this. Where you have multiple genes. So you have multiple genes, let's say 3 genes, and so I think the states are that the 0 gene binding a transcription factor, here 1 gene binds a transcription factor, here 2 genes, here 3 genes, but there is a finite number of genes, and it's infinite in this direction. And she somehow glued this space together from this shape. Something like this, and then she just figured out that if you want to cross all of these happen to satisfy, so these little bits satisfy the proportionality condition. Or something like this.
What was the network sheet? So, yeah.
I'm just coming back. So
That
this is what I drew here. So a finite number, let's say 3 genes. And so originally she did it with a cut here, so that it's a finite system that she did.
How do you, okay, so it's not that reaction network anymore. It's that reaction network with some conditional cut.
Yes. The other case is so it's easy because it's only unimolecular, so you have the explicit solution, and then
I mean, I guess I'm just, this is deficiency 0.
maybe yes.
So is that why the ratio holds? Because we're dealing with Poissons?
Yeah, so probably it holds because there is an underlying reason why the equilibrium is somehow simple, I think. Yes, so my suspicion is that that's the reason. But yes, maybe because the product forms is true. Okay. So here is another open question. So there is something called retroactivity, and if you have heard of Domitilla Del Vecchio at MIT, she's somebody who studies this, this comes from electrical modules. So when you combine integrated circuits or something, and so you have a specification for one, for the other, and you combine them and they do something different, what you suppose that they would do. And the same happens with biochemical modules. So you have one module which you think you understand, you have another which you think you understand, and you combine the two together, then they just don't behave how you expected them to behave, I think, because the downstream one, so there are molecules which are used by both, and so the downstream one will use molecules from the upstream one, and so it will distort the equilibrium distribution of the upstream system. And so then the question is, so I was gluing here chains at 1 and 2 states, but this is ridiculous and trivial. So the problem really is what happens when you have two biological modules, one with K and the other with L chemical species, so then the state spaces are then to the K and then to the L, and then you combine them, so that you combine them meaning that there are shared species, and so you combine them into an n to the power of m, where m is less than k plus l. And how can you compute the equilibrium distribution? And I have no idea, so this is hopeless, I think. And we're running over time. I can talk a little bit about it, but let me just show you the acknowledgement slides. So I started this work while I was at UC Santa Barbara with Mustafa Camacho and Joao España, and I was funded by the NSF. And then over the past 4 years, I've been working with Peter Pfaffer-Hubert, funded by the Humboldt Foundation and the Oxford Research Fund. And this is my website and the 2 papers that I've talked about. And if you're interested, I can talk about something that this is really interesting. So I sent an email about a week ago to somebody called Dave Doty at UC Davis, who is working in what kind of computations you can do with chemical reaction networks. And very kindly, he sent me a really exhaustive emails about all kinds of things. So I would love to talk about this, but I've run out of time. So if you are interested in it, just stay and I'll keep talking. If not, I don't know. You can ask questions now. Are there any questions?
I mean, do you have an example in real life where you can see that what you have produced here allow to better understand, situation in biology where you have, you can see, for example, how you glue these two, yes, for example, this part here, where you have, real system that you say, okay, now I can use this analysis and I predict that, this reaction or whatever I have this, and this can be used to understand and predict
so, unfortunately not. So, as I said, earlier I had this summary slide where I compared 4 gene regulatory systems where the analytical calculations gave some kind of signal response, so response to a stimulus, input-output conditions. And then I thought of scaling it up by combining larger chains, and then the moral of the story is that it's really hard. So even gluing together 2 Markov chains, even doing some testing. So what I understand say is that if this is your X8 chain, and X3 is this chain, and clearly this is taken to this, and this taken to this. So that is an example that is equivalent to having one state here and binding 2 places. So this gluing is equivalent to that. And even this small perturbation is somehow hard to compute. It's not easy. And like I said, these are very simple transformations.
And also, you pay a lot of attention to distribution equilibrium.
Yes.
So what we have found in the last couple of years is that it turns out that the probability of steady state probability, for example, suppose you send your molecule from the left, you have a hole from the right, and now you have all your binding. So you wait infinity. Now you can ask, all right, what's the probability that your gene or your whatever binding site has been activated. Or, for example, if you have 10, so you can ask what is the mean number of activators from, and this turns out you have to analyze properties, not at equilibrium, but there is no time now because you're looking at infinite behavior, and still you may be able to use some of your framework to say things about this. Have you looked, for example, what we looked at because we're interested in this is about time to a threshold or probability that the threshold has been reached, which is important in biological applications. So you could use some of your technology, some of your methodology that you have developed, not only to address question about, steady state, which is give you one type of information, but also give different type of information, like the probability of something to happen, from 0 to infinity, it's like fluxes. You could. Have you looked also into this kind of question?
No. Okay. So my answer is, one of the things I learned doing this is that it's just really hard, even though I'm just computing equilibrium distributions. So my example where I computed these dimers binding to a gene and how likely it is that the gene is in the bound and in the unbound form. I use this trick of writing a Cauchy product and doing a Cauchy integral and so on. And this is very ad hoc to that particular problem. Oh, the network was deficiency 0, and so that deficiency 0 theorem applied and so on. And so even these systems are really hard. So that's what I'm saying.
So maybe what I'm saying is that maybe you have to abandon your philosophy.
Yes.
That you want to have something, asymptotically. So that you can have something hybrid, where you push the calculation to some point, apply something to an example where you can say something significant, and there are a lot. If you abandon your hat of pure mathematicians and take another hat of doing some approximations, there may be here some nice connection to reality. We faced many cases where we looked at, for example, the genes that had to bind to 4 binding sites, and you have to add, this messenger RNA where you are in between here, the continuum and the discrete case.
Sure.
And still, nobody knows how it works. For example, some genes say, you go up to, let's say, everything is activated to nothing is activated. It's not clear that it works like this. So using some of your methods, again, maybe you have to abandon, the idea of going through all these asymptotics. But at some point, Maple can finish the calculation for you. You can have insight into biological questions, not stay just in one world.
Yes. On the other hand, I must say that my core skill is mathematics. So
I understood.
Sure.
There are other questions where you can look at this probability, looking at path in graphs and counting, paths, and this is equivalent as the method you mentioned when you have combinatorics. You have to find, the sum using expansion of generating functions, and you ended up doing more or less the same thing. That's just my comment.
Okay. Is anybody interested in Turing machines?
I'm interested, but I can't listen now. So
Oh.
I vote we postpone that conversation.
Okay. That's,
Okay,
thank you.
thanks.
Thanks.